Okay, so we said that if f is a continuous function on AB, then we know that capital F usually refers to the antiderivative. Okay? So anytime you see a capital F, you want to probably think antiderivative. So F has, what's that? In the case of like a polynomial, F would be like x cubed, and the little f would be like 3x squared. It has less degree. So capital F is the antiderivative, little f is the derivative. Okay, and then we said that if you put a d dx in front of an integral, like this, it feels like all you're doing is plugging in this x right here. So this just comes out to be f of x. And we actually proved that in the last lesson. We did a definition of derivative and tried to prove that. It was a little bit difficult toward the end. We had to recognize there's an average value function going on there. If you couldn't follow that proof, that's okay. In college, you might have to learn it all over again anyway. Or your professor will just skip it. Okay, but what this shows us is this. This is really important. The d dx and the integral symbol effectively seem to be sort of undoing each other. And f just sort of pops out. And so we see that integration and differentiation are inverse operations. So integration and differentiation are inverses, which you already knew because I keep saying it, but here we're formally writing this down. Okay, so these problems are a snap. You literally take the x and plug it in. The answer to this is cos x. Here you have two values of t, so you're going to stick it in for both. So this comes out to be x over 1 plus x squared. You'll notice that the lower limit of integration plays no role at all. See? In the first problem there was a negative pi there, but it had nothing to do with the answer. And in the second problem there's a 0 there, but that had nothing to do with the answer. So that's very interesting. And if you look at our proof, one of the last steps in our proof involved taking a derivative, and there was a constant. It went away. So it's just not manifesting itself at the end of this problem. So that's good. You get to ignore that. Okay? Now this next problem doesn't look like the same question, but it is, because it's giving you y, and this is crazy like integral thing, right? That's your function? Are you kidding me? Well, we're planning to take the derivative of it. So don't be scared of the integral sign. We're taking the derivative of y, see? So just reading the question, we see, oh, we're doing dy dx. So we'll just basically put a d dx in front of this thing. And we realize, oh, this is easy. I'll just basically plug this in. Okay, so you're definitely on the right track, if that's what you're thinking. But the chain rule is part of every derivative problem. Right? We always do the chain rule. Always. There's never an exception to that. And technically, you just differentiated with respect to x, but the inner function was x squared. See? So we need to attach a 2x to the end of this. It's part of the chain rule. Okay? So we can see that from this last example that the chain rule really does play a role in these problems. Now it didn't show itself in the first two examples because we were dealing with just x at the top, see? And the derivative of x is just 1. So I suppose you could have multiplied by 1 as an afterthought in keeping with the chain rule, but it certainly is silly to do that. Like putting times 1 here, times 1. That's unnecessary. But on that third problem, it is very necessary to have that. Okay? Okay. So let's update our little FTC rule, fundamental theorem of calculus. Let's write it this way. d dx of an integral is actually f of that thing times the derivative of that thing. So I wrote that here for you. This is a little bit more nouveau. It's updated. Okay? So it's f of x times u prime of x, where u prime is that upper function. All right, I'm going to go ahead and clear the ink and go to the next part here. what would we do with a problem like this one? Find dy dx if y equals the integral from 2x squared to x cubed. Notice there's no constant at all in our limits of integration. See that? So this problem is just a little bit different. So let me try to help you understand it geometrically. Okay? First of all, there's this function, right? And I don't need to draw 3t sine t for you. Okay? Let's just imagine any function. Just any f of t, all right, some random function. This is not this f of t, but it's any f of t. And let's imagine you were trying to find the area between 2x squared and x cubed. Okay, that's kind of weird, but I suppose those are just two spots on the x-axis. Okay, so I guess this is 2x squared, and this is x cubed. I'm assuming x cubed is bigger, although that might not be the case if you're between 0 and 1 or something. But let's just draw this to help us understand. We're trying to find this area in blue. One thing we could do is we could find the area between 0 and x cubed and the area between 0 and 2x squared and subtract them. We could do that, couldn't we? That would give us the blue area. So imagine taking the red area between 0 and x cubed and the red area between 0 and x squared and 2x squared and subtracting. That would give you this. So in other words, I want to rewrite this problem so it looks like the previous ones. It's actually two of them in one. This can be written like this. The integral from 0 to x cubed minus the integral from 0 to 2x squared, both of which can be solved according to the rule above. Okay, so this becomes substituting in the x cubed. Notice there's two spots for it. Each t gets one. So we basically get 3 times x cubed sine x cubed, but the chain rule requires a what? A 3x squared, right? Okay, that's from the chain rule. Minus, okay, now let's do the same thing with this second integral. I forgot to write the ddx's, guys. Let me put those in red. We're doing ddx here, aren't we? So dy dx is the derivative. I forgot to write that step. But we're taking the derivative ultimately after splitting it up. Okay, so this second integral, again, we're plugging in the 2x squared both here and here. So we're going to get 3 times 2x squared times sine of 2x squared times, and what does the chain rule require of us? A 4x, right. In other words, we just saw that we can actually make our FTC even more updated, even more nouveau, even better and improved by following this basic pattern. Anytime you're taking the derivative of an integral and there's two functions here and here, you can find it by doing f of b of x times b prime of x minus f of a of x times a prime of x. This is like the most general form of the FTC rule. So if you memorize this one, you're good to go. It actually works even when a and b are constants, but it even works when a and b are functions. And they can be as awkward as you like. They don't get any harder than that one. Okay? So memorize this formula. It looks sort of like a, I don't know, almost like a product rule. But it actually has to do with areas, as I tried to show up above in blue and red. Okay, this next problem, you'll see, you might see it on the AP test. You'll definitely see it on my test. And it's kind of a unique question. It's saying, let's try to create a function that has this derivative cotangent x. So that seems like a really unfair question, because I taught you the derivative of cotangent x, but I never gave you any functions whose derivative is cotangent. You can go back through all your notes. You will not find one. So how in the world can we do this? It's like we're trying to find an antiderivative or something. What is y if the derivative is cotangent x? Well, we can at least start with this. We know that y will be the antiderivative of cotangent x. And I don't want to use an x here. I'm going to keep my dummy variable as t, but you can use whatever letter you want, first letter of your first name, whatever. I know that this represents sort of the antiderivative of cotan. I guess that's kind of what we're looking for. And then we'll put an a and an x here. Here's why I'm putting an a and an x here. Watch. If I slap a d dx on both sides right now, watch. Don't do it, but I'm going to. Watch. d dx here, d dx here. What's the right side? Cotan x. Yeah, you just substitute the x in for the t. See what I did there? Okay, so I'm going to erase the d dx's. This is my function. When you differentiate it, sure enough, you get cotan x. So I'm off to a pretty good start. Okay, and then there's a mystery constant. In other words, there could be a 1 million here. The derivative would still come out to cot x. See? And now I just have to satisfy these conditions. I really want it to be where when x is 2, y comes out to negative 3. Let's see if I can get the conditions to work. In other words, I'm going to have to pick an a and a c that actually makes sense here. All right, so let's see. I want y to be negative 3 when x is 2. So when x is 2. How in the world am I going to guess what a and c are? Actually, it's really easy. If I make a 2 right now, what's going to happen?
0 out c from -3.
This integral is going to vanish. Isn't that true? If I make a 2, the area between 2 and 2 is exactly 0, right? So I'm just going to force a equal to 2. Watch what happens. It's going to look like this. It's going to be integral from 2 to 2 of cot t dt plus c. This will then vanish completely, and I get c equals negative 3. In other words, I want a to be 2, and I want c to be negative 3. Here's my final answer in blue. Y is equal to the integral from 2 to x of cot t dt minus 3. What's really cool about this function, I know it's a weird answer, but this is a cool function because if you take the derivative of it, it gives you cot x. But if all you do is plug in 2 into here, you get negative 3. So it satisfies both conditions. Notice the answer has an integral in it. That's the answer. But if you put a d dx on both sides right now, it'll all boil down to cot x. If instead you decide to just plug in 2, it comes out to y equals negative 3 if you plug in 2 for x. Pretty cool. Okay, we're actually almost done with this lesson. We're going to do one question that first period brought up. They were doing the assignment and they didn't know what the phrase total area meant, and I'm glad they asked. Some people just, flip your paper over, some people just thought, oh, I'll just basically do this on my calculator. Thinking that gives us the area under the curve, right? And the calculator gave them the answer. I think it's like 32/3, I can't remember. They looked in the back of the book and they're like, that's not right. Back of the book's wrong or something. Then they did another one and the back of the book was wrong again. Actually, the student was wrong here. When we do this, sometimes our book is wrong in the back, but when we do this process, understand that it gives us not the total area, but the net area under the curve. Remember? So, for example, we know this graph looks like this, actually. This is actually my favorite function. Do you have a favorite function? This is f equals 4x minus x squared. If you factor it, it definitely has roots at 0 and 4. Okay? So when you take the integral from 0 to 5, what happens is you collect all this positive area and then a little bit of negative area when you go out to 5. But the problem asks for total area, not net area. Okay? So what we should be doing in this problem is not running one integral from 0 to 5, but rather to get all the area to contribute as positive geometric area, we want to find area from 0 to 4 first. Okay, get an answer, this blue ball. Then we'll find this area, and even though it's negative, we're going to add it on to this one. So we want the combined total area. That's what that phrase means. Very, very important in the AP test. Okay, so it just looks like we're going to have to do this in 2 stages, basically. You're going to go from 0 to 4 first. And then you're going to go from 4 to 5. Unfortunately, it's going to produce a negative area, so I'm going to put an absolute value on this to prevent that. This is absolute value symbol, big absolute values. Sorry, I kind of ran out of room there. I'll put them in red so you can really see them. We know that area is negative and we don't want it to be. So let's try this problem now. So we want to find an antiderivative. Can you think of a function whose derivative is 4x? Yes. All right. 2x squared. Good. 2x squared does have derivative 4x. You're right. Can you think of a function that has derivative x squared, Kevin? 1/3 x cubed. Yes, we know it's cubic. And the leading coefficient has to be 1 when we take the derivative. So typically with these little dice, if you want to find antiderivative, you can just add 1 power and then divide by the new power. So this bumps up to x squared, and then you divide by 2. Here this bumps up to x cubed, and then you divide by 3. Okay. So there's your antiderivative. And we're going from 0 to 4. And then we have our big other answer here. This is the same antiderivative. It's still 2x squared minus 1/3 x cubed. This is between 4 and 5. And you just plug in 4 and plug in 0 and do a difference. So if you plug in 4, you get 2 times 4 squared minus 1/3 times 4 cubed. If you plug in 0, well, you just get one big fat goose egg. It's just 2 times 0 squared minus 1/3 times 0 cubed. You don't even have to write that. That's the first integral. In other words, the first integral comes out to 32 minus 64/3, which is 32/3. Okay. And then the second integral, I know it's going to come out negative, but I plan on absolute valuing it when I'm done, if that's a verb. Plugging in 5 and then 4 basically gives me, plugging in 5 gives me 2 times 25, so that's 50, minus 125/3, so I just plugged in 5. And plugging in 4, I calculated that earlier, it gave me 32, if you remember, from back here. I circled it in blue. So this is a little bit awkward, but I'm doing basically 18 minus 25/3. I kind of ran out of space, so I already did, I already plugged in 4 earlier, and I got all this junk, which was 32. And so I knew I was going to have to plug in 4 here, so I just abbreviated to 32. I wish I had more space.
13 minus 64/3, though.
What did I do wrong?
When you plugged in 4, you got 32 minus 64 thirds.
Yeah, which is 32/3. 96/3 minus 64/3 is 32/3.
But you just put 32.
Yeah, but this is the 32, and this, I don't know.
Oh, that's a 0.
This is 0. What is that? What is that?
That's
64/3?
That's the 1/3 4 cube.
Ah, I see it. I see it. Okay. I had no idea what you're talking about, to be honest. Yeah, sorry. This is 32/3 right here, is what you're saying. Yeah. You're right. All right. See, you know I can't do arithmetic. Okay. So we have 32/3 here. There's a plus 50. There's a minus 125/3. This is all in absolute values, this second part. And there's a minus 32/3 here. Okay, so all of this, I believe, just comes out to 13 in the end, if I'm not mistaken. Be careful to actually do the absolute values after you do your arithmetic. So on the inside, get this all figured out, and then do the absolute value, and then add it on to that. Because sometimes people just try to do absolute values whenever they want, and they get the wrong answer. Is there a way to make the calculator do this correctly the first time? Because the kids who got the wrong answer were doing it by just typing this, you know? And it's no wonder subtract it off, see? So can you think of a way to type it so that the calculator would not be confused?
Absolute
The
value.
integral of the absolute value of
Yeah, if you put this expression, the integrand in absolute values, what'll happen is the calculator will reflect, it'll reflect the negative pieces up above before it tries finding areas. So it would look like this, and those two areas would be like this, see? And then the calculator will do it perfectly the first try. So if you type it with absolute values, the calculator will do these for you. But you need to know total area and how to break it into two integrals like that. Okay, that's the end of the lesson. That gives us about 35 minutes for you to work on your midterm. You can work on your homework. We can answer questions on your worksheets due today, whatever, okay? So